This is your lesson on matrices. We'll introduce what they are, how to add, subtract, and multiply them. It'll cover Glencoe sections 4.1, 4.2, and 4.3. The first example that I'm going to explain is how to organize data into a matrix. Notice that the question actually provided for me tables. Whenever I'm given tables, I actually like to just leave the tables the way they are and use those to help me create my matrices. So you'll probably notice that my answer is going to be a little bit different than the textbooks. So I'm going to create a matrix where it's going to give a column for the metro cable and then a column for the cable city prices. Okay? So the very first row is going to represent the basic service. So it's $11.95 for metro and it's $9.95 for cable city. The second row is going to represent standard services, and it's $30.75 for metro and $31.95 for cable city. Now here's where you actually need to read the data. It says premium channels in addition to standard services. So that right there tells me that I actually need to add whatever the amount was for standard services to that additional charge. So for metro cable, I'm adding $10 to $30.75, giving me $40.75. And for standard services, I'm adding $8.95 to $31.95, and that's going to get me $40.90. Okay, so this row represents with one premium. Then we're going to do a row for 2 premium and a row for 3 premium. So once again, I'm going to add that amount to the standard service cost. So when I add 19 to 30.75, I get $39.75. When I add $16.95 to the $31.95 for cable city, I get $48.90. And then the last one are the 3 premiums. And I'm going to have 25 plus 30.75, giving me $55.75. And for cable city, $31.95 plus that additional charge of $22.95, giving me $54.90. Okay. Now the question did ask for me to find when is each company less expensive. Because all my data is organized into a nice array, I get to just simply circle. I can literally just see and compare the numbers and see who is the least expensive at whatever the service is that I'm looking at. Although I didn't catch my mistake earlier. My metro cable, 19 plus 30.75, that's $49.75. Ooh, careful there. That would have totally changed my answer. So the conclusion that I can draw is that metro cable is least expensive for standard services as well as when you add one premium. And then cable city is actually more cost effective in the other 3 categories. We're now going to look at the last 2 examples for 4.1. The first example deals with the dimensions of a matrix. The dimensions of a matrix are read as rows by columns. And hopefully you've learned in maybe middle school, rows are horizontal and columns are vertical. They support a building essentially. So rows, I have 1 row, 2 rows, 3 rows. Now the number of vertical columns I have 1 and 2. Which is why I can say that the dimensions for matrix B are a 3 by 2. Okay? This is important when setting matrices equal to one another, when adding them, subtracting them, and multiplying them. So notice that in example 3, both of our matrices are 2 by 1. And so now we can set their corresponding elements equal to one another. So y equals 6 minus 2x. And then we also have 3x equals 31 plus 4y. One of the strategies for solving systems of equations is using substitution. So I'm actually going to substitute 6 minus 2x in for y. So 3x equals 31. I can barely read my iPad handwriting. Plus 4 times the quantity of 6 minus 2x. Now I'm just going to simplify my expression here. I'm going to distribute in my 4 to both of my terms, getting me 24 and a negative 8x. I'm going to combine some like terms here. I'm going to carry on up here. 3x equals 55 minus 8x. Now I'm going to add 8x onto both sides. I can isolate my variable. 3 plus 8 is 11, so we have 11x equals 55. Divide by 11. So we get x is equal to 5. Now, unfortunately, we're not done yet. We still need to solve for y. I'm going to use the first statement, y equals 6 minus 2x, and I'm going to plug in my value for x. So we really get 6 minus 10, and 6 minus 10, well, that's equal to negative 4. Okay, you can also leave your answer in terms of an ordered pair. If you're noticing now, we're going to go into actually section 4.2. So notice that your vocab words for 4.2 will appear on the bottom of this example. Here we go. All right, looking at 4.2, the very first example, I am adding matrices together. In order for me to add matrices together, they need to have the same dimensions. So in A, I'm noticing that both A and B are 2 by 2s because they have 2 rows and they have 2 columns. So when adding two matrices together, I get to add their corresponding elements, okay? So what I can really do, if we want to, just pretend that these words are no longer here. Maybe I'll just cross them out for you, and I'll just write on top of them. Yeah, that's what we'll do. All right, so we're going to add these two things together. So I'm going to add, first off, the 4 and the negative 3. That'll get me the row 1, column 1 position of my solution. 4 plus negative 3 is equal to 1. Now, I'm going to look at my row 1, column 2 spot, and I'm going to add negative 6 and 7. Negative 6 plus 7 is equal to 1. Well, isn't that super convenient so far? All right, now, row 2. Row 2, we're going to add the 2 and the 5 because they're both the column 1 position. 2 and 5 gets me 7. Now, the last one, we have 3 plus negative 9, and that's going to get me negative 6. Okay? Now, I'm noticing that I forgot to label this B. I'll have to go in and change that. I'm noticing here for A and B, the dimensions for A, I have 2 rows and I have 3 columns. Whereas for B, I have 2 rows and 2 columns. And because their dimensions are not the same, they cannot be added. Alrighty, now let's look at example 2 where we are subtracting matrices, okay? It'll be treated just like we did with addition. They need to have the same dimensions in order for them to be subtracted, okay? And just like I did before, I'm just going to change that. That way I can just create my solutions, okay? Notice that the answer to a addition or subtraction problem gives you the same dimensions. So the first one, 9 minus 3. 9 minus 3 produces 6. Then we have 2 minus 6. 2 minus 6 creates negative 4. Next one, we have negative 4 minus 8. Uh-oh, can you deal with negatives? Negative 4 minus 8 gets you negative 12. And the last one, we have 7 minus negative 2, which really means 7 plus 2, which gets me 9. I find that it really helps if I verbalize these out loud. So if you're getting lost in the positives and the negatives, maybe it'll help just to say things out loud. Just a little piece of advice. All right, we're continuing still with 4.2, and now we're getting into some real-world problems here, where I've been presented with the number of endangered and threatened species in the United States as well as the world. It's also been organized based upon the type of animals. Well, like I said before, I actually just like to take the information and the data in the table and create a matrix with it. So notice that I literally can just draw brackets around them, and in this situation create a 5 by 2 matrix representing the world. I can do the same also for the United States, also again creating a 5 by 2, but in this one it's representing the United States. The question asks me how many more endangered and threatened species are there on the world list than on the United States list. So many more. I'm really looking for the difference between the world and the United States. So one way of looking at it is the world minus the United States, okay? So I'm just going to subtract the two matrices. So it might take me a second to rewrite them. That way I'm not going off the page here. And please humor my really not so wonderful iPad handwriting. So here is the world matrix. Okay, it's important to recognize that the columns represent the endangered and the threatened, and the rows represent the types of animals. Okay, might not be something you think you care about right now, but actually in the end, it's going to help us answer the question that's actually being answered. All right, so they're the same dimensions, and so when we go to subtract them, we're actually just going to subtract their corresponding elements. And finally, I have this written. Okay, so our answer is going to be a 5 by 2 as well. So we have 309 minus 61. 309 minus 61 gets me 204. Sorry, my computer screen popped up. 248. And then we're going to have 24 minus 8. 24 minus 8 gets me 16. This represents the number of mammals, endangered and threatened, the difference between them. So then we're doing 252 minus 79. That gets me 178. We have 21 minus 15. That gets me 6. This row represents the number of endangered and the number of threatened birds. Now we have 79 minus 14, and that gets me 65. 36 minus 22, that gets me 14. This is our row for reptiles. 17 minus 9, that gets me 8. And I don't know why I just chose a circle. 9 minus 8 gets me 1. Here are my amphibians. Last row, 80 minus 69 is 11. And 42 minus 42 is 0. This is the number of fish, okay? So all organized in one lovely list is actually the differences between the world and the United States endangered and threatened species list. So what you could literally provide to an employer if they asked you to organize the data. I could literally say this is the difference in endangered species. And then I could also say, well, this is the difference in the number of threatened species between the United States and the world. And you can even go into more detail about how this is mammals, this is birds, the bottom one's fish. There's no drawing of a fish, kind of looks like a bow tie. Okay. Example 4, I'm now going to multiply a matrix by a scalar. Scalar multiplication is different from matrix multiplication, as you will soon see. I'm given this matrix A, and I'm told to do 3 multiplied by A. So what I'm literally going to do is I'm going to take this 3, and I'm going to multiply each of my elements by the number 3. Okay, just using the distributive property. He's going to go in there to each of the elements. So 3 times 2 is 6. 3 times 8 is 24. 3 times negative 3 is negative 9. Now I'm going to that bottom row. 3 times 5 is 15. 3 times negative 9 is negative 27. And 3 times 2 is 6. This is multiplication by a scalar, and that is all we had to do. All right, we're going to finish up 4-2 with our last example where we're combining a series of matrix operations. I'm given matrix A and matrix B. First off, we notice that they're both 2 by 2, so we should be good for whatever they ask us to do. And I'm asked to find 5A minus 2B. So I'm asked to basically multiply A by 5 as well as multiply B by 2. And then I'm going to subtract the 2 together. So first off, 5 times A. I'm going to multiply each of these terms inside of A by 5. 7 times 5 is 35. 7 times 3, that's going to get, 5 times 3 is 15. 5 times negative 4 is negative 20. And 5 times negative 1 is negative 5. Okay, so here is 5A. Now we're going to do 2B. So multiply everything in there by 2. 9 times 2 is 18. 2 times 6 is 12. 2 times 3 is 6. And 2 times 10 is 20. And now I'm going to subtract these two matrices together by subtracting their corresponding elements. 35 minus 18 gets me 17. 15 minus 12, that gets me 3. Negative 20 minus 6, that gets me negative 26. And negative 5, give him a box, why not? Negative 5 minus 20 gets me negative 25. So that is all for 4-2. Now we're going to pick up and go to 4-3. Make sure you notice that there's definitions, again, separating the sections, okay? In example 1 of 4.3, I'm asked to determine whether or not the matrix products can be defined, aka whether or not I can actually multiply them. So something that I like to do, it's just a little bit of a test, I guess. I'm going to zoom in, if I can figure that out. Zoom in here. Looking at A, I have a 2 by 5 multiplied by a 5 by 4. Perfect. The innies and the outies. You can only multiply two matrices if their number of columns is equal to the number of rows. So the number of columns in the first matrix must be equal to the number of rows in the second matrix. Quick way, are their inner numbers the same? Yep, guess what? You can multiply them. So it is defined. The cool thing is, their outer numbers are going to produce the dimensions of their solution. So the solution of A times B will be a 2 by 4. Isn't that cool? So now let's look over here at B. Can these two matrices be multiplied? Well, when I do the inner test, the number of columns of A is not the same as the number of rows of B. Therefore, their product is not defined. Okay, now we're going crooked here, but look, that page is all done. All right, now we're going to look at example 2 where we're actually going forth and multiplying matrices. Good key thought here, square matrices can always be multiplied. The way we multiply matrices is we multiply rows by columns. And if it tells me to find RS, it's telling me multiply R by S. Now you're going to notice that I'm actually going to set this up a little bit differently than your textbook does. So here is going to be matrix R, my very first thing. And then slightly above him, I'm actually going to multiply, or we'll put what I'm multiplying him by, which is matrix S, okay? The reason I like to do this is because it actually creates a spot for me to create their solution. So my blue matrix here will create their solutions. So I'm going to multiply row of R by the first column of S. And when I multiply these, I'm going to do 2 times 3, which is 6, plus negative 1 times 5. Let me repeat that. 2 times 3 plus negative 1 times 5. So 2 times 3 is 6, negative 1 times 5 is negative 5. 6 plus negative 5 is 1. Now, I'm going to do the same thing. Row 1 multiplied by column 2. That's going to get me the answer for my row 1, column 2 spot. So 2 times negative 9 gets me negative 18. Negative 1 times 7 gets me negative 7. Negative 18 plus negative 7 gets me negative 25. Now we're going to move into row 2. Row 2 multiplied by column 1 is going to create my row 2, column 1 solution. 3 times 3 gets me 9. 4 times 5 gets me 20. 9 plus 20 gets me 29. Last one. Row 2 multiplied by column 2. 3 times negative 9 gets me negative 27. 4 times 7, that gets me 28. Negative 27 plus 28 gets me 1. Here is my solution. This is again just a different setup, and for me, I just felt like it was much more obvious as to which row and which column I was going to use to set up my matrix multiplication problem. All right, we're now looking at our third example of this section with a real-world problem where we're in a track meet and points are awarded for each of the place finishers, and we need to find the total number of points for each school to answer the question of who won the track meet. Like I've said before, I really just love organizing the data that they give me in a table already in a matrix, okay? Notice each of my columns represents the places, and then each of the rows, the schools, and each of the elements represents the number of finishers from that school in that place, creating a 4 by a 3. Now, I'm also told points that are awarded for each of the place finishers. So realistically, what you want to do here is say, okay, 5 points for every first place. 8 times 5. Oh, now I need to add 3 times the 4 for the second place, and then 5 times the 1, and I'm going to add them together. What does this sound like? Well, it sounds like matrix multiplication. And to multiply a 4 by a 3 by something, whatever I'm multiplying it by needs to have 3 rows, because the number of columns of the first must represent the number of rows of the second. So whatever I'm creating that I'm going to multiply him by must have 3 rows, and it doesn't matter what number of columns I have, but if we're thinking about it, we want the total number of points for each of the schools. So the product will be a 4 by a something. I don't care if it's the individual columns. I want the total. I only want one element for each school, because that's going to be the sum of their points, okay? So that's why we're going to multiply it by our point matrix, where we're going to have the first column represent, or I'm sorry, the first row represent the 5 points for the first place finishers. The second row represent the 3 points for the second, and the the third row by the 1 pointer, okay? So 4 by a 3 by a 3 by a 1. So I'm going to set it up just like I did previously. Don't worry that they have different dimensions. You won't always be given 2 by 2s by 2 by 2s. I'm just going to set it up the same way here. So rewriting all of this data. So there's my 4 by my 3. And now I'm going to multiply it by my 5 by my 3 by a 1. And the product is going to be a 4 by a 1, where each of the school's total points gets its own row. So it'll be pretty clear to me as to who won the meet, okay? So notice when we're multiplying this, okay? Rows multiplied by columns. My 8 first place finishers, well gosh, we placed it perfectly, get multiplied by the 5 points. So 8 times 5, that gets me 40. So then I'm going to have my 4 second place finishers get 3 points each, and that's my 12, okay? And then lastly, let's pick another color here. My 5 third place finishers get 1 point apiece, and that's 5. So then the grand total for Jefferson is 40 plus 12 plus 5, or you can say 57 points. Nice and neat, right? So now we're going to repeat the process, okay? So now we're going to do London. The 6 first place finishers get multiplied by the 5 points. So 6 times 5 is 30. Then we're going to switch to purple. The 3 second place finishers get 3 points each, and that's 9. And then lastly, at London, we're going to have the 7 third place finishers each get 1 point. So they get 7 points for that. And so then when we add them up, 30 plus 9 plus 7, we get 46 points. So far, it's looking like Jefferson's our winner. But we still got to do Springfield and Madison, okay? Springfield, they had 5 first place finishers. They each get 5 points. That's 25 points. And then we're going to each have 7 second place finishers, and they get 3 points apiece. That's 21. And then we got their 3 third place finishers each getting 1, so there's 3 points. Add them all up, 25 plus 21 plus 3, that gets me 49. Uh-oh, Jefferson, you're pulling it off. All right, Madison, 7 times 5, 35. And then we got 5 second place finishers each getting 3 points, that's 15. And then here we go, 4 third place finishers each getting 1, so we have a plus 4. So here we go, 35 plus 15 plus 4, 54. So we get to say Jefferson clearly and by matrix operations won the track meet. All right, the last 2 examples of this section deal with the commutative property and the distributive property, and the purpose is to help you discover whether or not those properties hold true with matrices. So P times Q and Q times P. The purpose of A and B is to tell you whether or not they're going to get the same thing. So P times Q. The dimensions for P, we have 3 rows and 2 columns, and the dimensions for Q is a 2 by a 3. Okay, so first off, because the number of columns of P is equal to the number of rows of Q, they can be multiplied, and their solution is going to be a 3 by a 3. Just looking ahead a little bit here with Q times P, the dimensions of Q are a 2 by a 3, and the dimensions of P are a 3 by a 2. So just like before, the number of columns of Q are equal to the number of rows of P. Therefore, they can be multiplied. However, their solution will be a 2 by a 2. So notice that the dimensions of PQ and the dimensions of QP do not equal each other, which is why the commutative property does not hold true. Which is why if I tell you to multiply P times Q, I'm telling you to do it in that exact order, okay? So now let's actually multiply them out. So P, here we go. He's an 8, a negative 2, and a 0. And he's a negative 7, a 4, and a 3. And he's being multiplied by the lovely Q, so 9, 6, negative 3, negative 1, 2, and negative 5. Okay, once again, I just like this strategy because it just really frames up everything for me here. All right, here we go. Row 1 times column 1 will get me my row 1, column 1 solution. So we have 8 multiplied by 9 plus negative 7 multiplied by 6. Let me say that out loud one more time. 8 times 9, that's going to get me 72. And negative 7 times 6, that gets me negative 42. So 72 minus 42 gets me 30. All right, let's now do row 1 multiplied by column 2 to get me my row 1, column 2 solution. So we have 8 times negative 8 times negative 3, that gets me negative 24. And we have negative 7 times negative 1, that gets me positive 7. So negative 24 plus 7, that's equal to negative 17. Okay? All right, last row and column for this guy. Row 1 times column 3 will fill in that position over there. 8 times 2 is 16, and negative 7 times negative 5 is positive 35. 16 plus 35 gets me 51. Okay? Let's see if you can fill in the missing blanks here, and then check your solutions with your textbook. Okay? Let's start QP for you. Once again, I'm going to set it up just like I've been doing. We have our Q over here now because we were told to do a different order. And up here is going to be our P. 8, negative 2, and 0, and negative 7, 4, and 3. Okay? It's going to set up my nice little solution here where it's going to be 2 rows and 2 columns. Okay? All right. Row 1 times column 1. We're going to have 9 multiplied by 8. That gets me 72. Negative 3 multiplied by negative 2 gets me positive 6. And then we have 2 times 0, which is just 0. So 72 plus 6 gets me 78. All right, now we're looking at row 1 times column 2 to fill in my row 1, column 2 spot. So 9 multiplied by negative 7 gets me negative 63. Negative 3 times positive 4 gets me negative 12. And 2 times 3 gets me 6. So negative 63 plus negative 12 plus 6 gets me negative 69. Just like before, let's see if you can fill in the blanks yourself. All right, so we're going to look at A, which is a distributive property. First off, I'm just going to rewrite this first matrix A, 3, negative 1, 2, 4. Then I'm going to focus on this inside quantity in parentheses here, okay? So I'm going to rewrite my expression, negative 2, 6, 5, 7, plus 1, negative 5, 1, 3, okay? So first off on the inside, we have negative 2 plus 1. That's going to get me negative 1. Next, we have 5 plus 1 getting me 6. Now we have 6 plus negative 5 getting me 1. And then we have 7 plus 3 getting me 10. Okay? So now I'm just multiplying these two matrices together here. Okay? So we have a 2 by 2 multiplied by a 2 by 2, which is going to produce another 2 by 2. Okay? So first, row 1 times column 1. We have 3 times negative 1, which is negative 3, plus 2 times 1, which is 2. So our first spot is negative 1. Next, we have row 1 times column 2. 3 times 6 is 18, plus 2 times 10, which is 20, which gets me 38. Okay. Now, row 2 times column 1. Negative 1 times negative 1 gets me 1. 4 times 1 gets me 4. 1 plus 4 is 5. Last one. Row 2 times column 2. Negative 1 times 6 is negative 6, and 4 times 10 is 40. Negative 6 plus 40 gets me 34. Okay? All right, why don't you try B on your own and check your answer with the textbook.